Hello and welcome back, everybody. Today we'll talk about closest pairs, Chapter 3 in Computational Geometry. Before we do that, let me gently, briefly go back to a couple of things. First of all, as always, here's the chat where you can see what's happening. And don't forget, I can see what's happening. That is a good place to place your comments, questions, and whatever. That gives me the idea that I'm not just talking to some camera, but actually talking to people. And before we dive into this next chapter, let's do a couple of things for the previous chapter.
Let's talk about the convex hull. In geometry,
Just quickly stop that and start it again. Aaron Becker from Houston, who with his group does great things in robotics, and we work together quite a bit, do nice things, and it's really nice to see that several members of his group are following. He sent us pictures and as well. And Aaron is also a wizard with videos. Some of you may know that I've been doing videos in various kinds, but most of you don't know that Aaron was actually the one who got me started on doing videos with Camtasia, and he was kind, enthusiastic, and productive enough to produce a quick video about Graham scan. And without further ado, let me just quickly play that with his original voice.
let's talk about the convex hull. In geometry, the convex hull of a set of points is the smallest convex set that contains them. You can also define the convex hull as the intersection of all convex sets containing a given subset of a Euclidean space. An equivalent definition is a set of all convex combinations of points in the subset. I like to visualize the convex hull as a shape enclosed by a rubber band stretched around the set. In 1972, Ronald Graham published a delightful paper, An Efficient Algorithm for Determining the Convex Hull of a Finite Planar Set. The paper is just 1.5 pages long, but it gives an algorithm with time complexity O of n log n for n points. The first step is to find the point with the lowest y-coordinate. This is the starting point of the convex hull. If more than one point has this y-coordinate, the rightmost one is used. Second, all the remaining points are sorted by polar angle to the starting point. This can be accomplished without trigonometry by using the reciprocal of the slope, so the negative run over the rise, and using negative infinity if the points have the same y-coordinate. Call this list sorted points. The algorithm then considers each sorted point in sequence, which can be animated by moving the slider step. We maintain a stack called the convex hull points that is initialized with a starting point and the first sorted point. For every additional point in sorted points, we calculate if connecting to this point from the convex hull points required a left turn or a right turn. If a right turn was required, we pop points off the stack, convex hull points, until connecting to the current point in sorted points requires a left turn. The removed lines from convex hull points are drawn as dashed red lines. We then add this point to convex hull points and repeat until we have stepped through all the points in sorted points. The code is pleasantly simple, and you can see the stack operations for stepping through the sorted points here. We use the function isLeftTurn, which returns the signed area of a triangle defined by the points P, Q, and R. If the area is positive, then going from PQ to QR is a left turn. If the area is negative, it is a right turn. The area computation is the determinant of a 3x3 matrix, and so also requires no trigonometric functions. You can easily rerun this with different values of n and see that algorithm go through. You can also modify the points at any time, and you can see that convex hull stretches out. Enjoy!
Yeah, so thank you, Aaron. And as you could see, unfortunately, 2020 has been a pretty wild year. One of the people who left us this year was Ron Graham himself. I had the pleasure to meet him a couple of years ago at a workshop for about a week. Still very active, one of the closest collaborators of Erdős, frequent host, closest friend, and so on and so on. Yeah, so let's go back into that chapter. And when we go back into that chapter, you've been ready and prepared, locked and loaded for the quiz. And let me quickly switch over to that quiz to get this started. Here we go. Is it ready? Yes, it is. "11 players, 12 players, come on." "13 is bad luck, 14 is better. The more the merrier." And again, the magic chocolate, waiting for whoever wins this. 16 looks like a good number. You have seen the questions. Let's get started on that. Question number 1. What data structures are particularly helpful for carrying out gram scan? A sorted list, a stack, or both? Ooh, quick responses. And the answer is, indeed, it's both, because you need the sorted list. That's what you do in the beginning when you do the sorting, the computation by, what's going on here? By angle. Then the stack, of course, is when you follow along the left-hand turns. You need both of them. Both are used, and that's what you do. Let's see what happened. Jan, Ramin, Markus, Felix, Dan, Torben, Abhinav, Alex, Aaron, Florian. Oh no, what happened? Somebody else also must have mistyped, but oh well, it's not the end of it. Second question. Question number 2. Answer fast to get more points. What is the most expensive phase of gram scan? Finding the point with lowest y coordinates, sorting points by polar angle with respect to p, carrying out the scan, and deleting right-hand turns. What is it? And the answer is, of course, the sorting. Once you have done the sorting, we'll revisit the sorting today, and we'll talk about complexity and n versus log n log n versus n again. And that is, of course, correct, and we'll see how that affects your points. Jan, Ramin. Oh, Jan was quick. Oh, it's all very close. 3 points ahead of Ramin and 9 points ahead of Markus. Only 11 before Felix, Torben, Abhinav, Dan. There's Dan. And Aaron is there. Oh, Aaron is there. That's great. The purple Aaron. Let's see. Next question. How many of the discussed algorithms can have an arguably better time complexity than gram scan? Of course, the word arguably is an issue here. And the answer is 2. Because, well, what does it take to be faster than O of n log n? We know that we cannot do in linear time, but there was this issue of n log h. And there were 2 algorithms. One was the ultimate by Kirkpatrick and Seidel. And the other was, of course, chance algorithm, which got us also n log h. And the others were slower. I mean, there was quick call, which doesn't really get a subquadratic guarantee. We also had Jarvis March, and then of course Preparator Hong. So 2 out of 5 is the answer here. What happened? Okay, Alex, Torben, and Abhinav dropped some points. That mixes up the field. Jan is still holding the front, but he's been joined by the magic unicorn, Ramin, with the same number of points. They're actually tied in first place. Markus behind, Felix, Dan, and Aaron. Not too far behind, slow but steady. We'll see how many more he can pass by giving the right answers. Question number 4, the median question. Chance algorithm is based on combining the ideas of which 2 algorithms in a really clever way? And you see the combinations. You saw the combinations on the sheet. And the answer is, of course, Gram-Scan and Jarvis-March. Gram-Scan was what you used for doing the computation of the hulls of these small subsets of size m. And then you did the basically the gift wrapping of these subhulls by doing the right way, and we'll have some more of that in the next question. Let's see what happens. Jan, Ramin. Oh no, Markus and Felix drop points. That mixes up the order. Jan, Ramin, Dan, and Aaron. So we got 2 from Braunschweig, 2 from Houston. Markus, Alex, Torben, Abhinav is still here in hot pursuit. Felix and Nick with 1 dropped question each. So here we go. What is happening here? 1 point between Jan and Ramin, a few more points to Dan, and Aaron with, well, just 50 points behind Jan. What does that do? Next question here. Number 5. Which of the following steps is not part of chance algorithm? Find extremal points, partition the point, set into subsets of size m, use Jarvis-March to compute the convex hull of the subsets, find h points doing points along the convex hull, use binary search for identifying targets. That's a little sneaky, I must admit, but the majority has not been fooled because it's not Jarvis-March that we use for these subsets. We use Gram-Scan. We use Jarvis-March for, or something similar to Jarvis-March for the gift wrapping part. That's the second part. Okay, what happens? Oh no, Houston, you have a problem. Oh my goodness. Aaron drops, and Aaron and Dan drop down the rankings, and we have Ramin and Jan still close, tied up ahead, 6 points, just merely 6 points. We'll see if we need a recount for that. Torben, Markus, Abhinav, Felix, Dan, Nick, and Aaron. But we still got 2 more questions, so we'll see what happens. Number 6. Answer fast to get more points. How do we determine the critical parameter h in chance algorithm? Setting n equals to h, enumerating possible choices, performing an exponential search, performing a doubly exponential search. What's it gonna be? What do we do? Aha! Okay, still the majority got it right. That was a little sneaky. Of course, we do set m equals to h, but that doesn't resolve yet what h is going to be. So that's one step that we do. And then there was a second little snippet of algorithm where something happens. And it's not just all choices. It's also not an exponential search. It's a doubly exponential search. That is important. So we don't just double the value in each step, but we sort of take a 2 to the 2 to the t. So we really cast a wide net, and because that means we only have a very limited number of trials we do, it is just enough to get this complexity. If you check this again in the slides from the last lecture, you see that there's this 2 to the 2 to the t, and that works out the right way because you put the log in there, and then everything works out fine. Okay, what happened in the rankings? Oh no, oh no. Ramin is fastest and got the points, and Jan dropped the points, and Torben, Abhinav, Felix are still a little behind, but at this point Ramin is the only person who's got all the right answers. And looking at the scores here, I think he's pretty much clinched it, unless Jan can basically answer the last question correctly in 0 time, which means he has like 996 points, at least 994, I'm sorry. And this is still very close. So Ramin can feel pretty comfortable, but of course it's a matter of pride that you don't say like, okay, I got it, but I want to get the last question correct as well. Jan, Torben, Abhinav, Felix are still in the running, and see how this happens. A little while ago, Houston was in hot pursuit and close to the top, ready to top the podium, and now they slipped up a little bit, but they're still great guys and they know their stuff, I know that. All right, last question. Last question, question number 7. Are you ready? Go. Answer fast. Consider a set of n line segments in the plane. What is the best runtime for computing the h line segments that form the lower envelope? That is arguably the trickiest of the questions, and of course that did require a bit of, okay, correct guessing. Yeah, you did guess right. The answer is O of n log h. And in case, well, you can ask, like, how did you find this? How did you find this? This is actually in the paper by Chan. There's a specific section in that paper, in Chan's paper, yeah, and Marcus has it probably, I don't know, where there's a section that mentions this. But you see here line segments and lower envelope. Even if you don't know what a lower envelope is, you can read it in the paper, and of course you can research what's going on there. So you have a set of line segments, limited length, and then which is sort of the bottommost of these. And that is similar to computing a convex hull, and there's a few subtleties that Timothy Chan mentions in his paper. Right, let's see what we got. And we have a winner by knockout, followed by Jan and Abhinav. Good job there, Abhinav. You were a little behind, but you didn't give up, and you actually got within 10 points of the silver medal. The bronze is still really good. And Felix also not too shabby here. And the others here, well, thanks for being part of this. Thanks for participating. You can tell this is getting a little more challenging, but the fact that most of you got most of the answers is a good sign, because that's obviously the real win, is gaining knowledge and understanding what's going on and thinking about these things. So, Ramin, you can claim your chocolates. Next time we meet in person, who knows when that's going to be. Excellent. That gets us to the next part here. The next part being today's lecture. And here we go. Yeah, so you see, we're dealing with points, with lines, with objects. Many of them are in the plane. And obviously, geometry, computational geometry started out, if you want to think about it that way, with the old Greek trigonometry, where you do actually do some constructive geometry in the plane, angles, lines, triangles, stuff like that. But of course, we're doing these things with a computer. That's where the linear algebra comes in. So most of the classic computational geometry is in 2 dimensions. There's some which is in 3, but when you draw stuff on the line or when you construct things on a screen, 2D is an obvious good choice. Also, 2D is quite challenging by itself already. But when you go beyond that, you will see, of course, that 3 dimensions is a natural question. How would you encounter higher dimensions in geometry, higher than 3? Well, it turns out that data with many parameters can be described by sets in higher dimensions. Towards the end of this lecture today, I'll wave my hands over some things in higher dimensions to get you started and primed on thinking a little further. But let's start out things gently. And here we go. Yep, so there are a few things. The problem we're going to consider is called closest pair. So you are given a set of points in some potentially higher dimensional space. Here's a set of points, so let's look at those. This set of points here. And what you want is a pair of points among all these points that has the smallest distance. Well, when you look at this closely, you see that's a point here that has the smallest distance. I mean, that looks that way. Of course, it depends a little bit on what you are actually seeing and how you're measuring these things. When you're in high dimensions, that could possibly change a little bit. There could be some other metrics, some other ways of measuring these distances. We'll talk about that in a moment. But when you look at this set of points, there are different ways of computing distances, and there are different ways of comparing all these distances. Which of them has the smallest distance? Now, it's not so difficult to see that. You can do this in quadratic time. Look at all the pairs of points, and one of them is the closest. Obviously, you assume that you can compute these and compare these distances, but getting a quadratic runtime is really easy, doesn't take much. But if you're in data science and you have really, really large sets of points, you definitely don't want to look at all the pairs, because that can be for millions of points. That would be trillions of pairs, and that's definitely too expensive. So let's look at a few of these things and work our way towards some algorithms that do a better job than n squared, do a better job than doing brute force, quadratic, all the pairs. And along the way, we will encounter a number of different issues, a number of different concepts. First of all, we'll talk about ways of measuring this. And of course, we'll also talk about, along the way, about various algorithmic approaches, paradigms, ways of computing and achieving good runtimes. We'll get to that bit by bit. And obviously, as always, you will see and you will encounter a number of classic, famous papers, which you'll see pretty much in the original. The original ones will be posted on the website, so you can look at it for yourself, see how not just computational geometry has developed, but also how typesetting has developed over time. But also, it gives you a good idea of some of these paradigms and some of these general techniques and approaches, which will allow you to use some of these techniques for other problems in other contexts. So one by one, measuring these distances, let's look at how we measure these distances and how we describe this. I mean, if I throw this at you, basically you're looking for a pair of points for which this distance is the smallest one for all pairs of points which are distinct. Now, of course, if you make the pair of points which are the same, then the distance is 0. One other thing when looking at this notation, you see here there's a d up here for the dimension, there's a d up down here for the distance. Of Of course, you can consider like changing these letters to make them unique and distinct. I've debated doing that, but that's what happens in literature. That's how people just choose their numbers. D is for distance, D is for dimension, D is for distance. So people may reuse the same letters. And of course, you're all smart enough to sort of keep these things apart and make sure that that's not a distance and that's not a dimension. All right, let's look at these distances and let's see how we actually define this and how we describe this. Now, we're going to measure this by some function that sort of takes each pair of points and maps it to a non-negative number, which is a distance function. Now, a distance function is not just something that gives a weight or some cost to any pair, but it has to satisfy a few properties, a few things that really make it a proper metric, as opposed to just an arbitrary weight. First of all, there's this issue that the distance between 2 points can only be 0 if it's actually 1 point. So a point to itself has a distance of 0, but that's the only way of how a distance of 0 can occur. Any 2 points which are distinct, see that says greater or equal to 0, so cannot have distance 0, so there must be a positive distance. That's sometimes also called definiteness. That has something to do with matrices, positive, definite, semi-definite, and so on. In that terms, that's not going to be a fundamental part of any exam or so on, but I'm going to mention it anyways. Okay, that's one. So you always have a positive distance, and you can only have a 0 if it's the same point. The second is it's symmetric. So if you go from x to y, and if you go from y to x, that is symmetric. And it says symmetry, see that? That's geometric distances. Of course, in some places in physics or in real life and so on, you can have a distance from x to y or from y to x. If you go downhill or uphill, that could have different costs at different time and so on. We're just looking at relatively simple distance functions, which are called metrics. Now, here's a third one, which is of fundamental importance. It says if you go from x to z, but you go via y. So you go from x to z here, and first you go to y, and then you go from y on to z. So if instead of going from here to here directly, you do a detour, go up here and go down here, that does not get shorter. That's of course called the triangle inequality. So if you have a triangle, then the direct connection is not longer than taking the sum of the other two edges. And anything that satisfies this is called a metric, and anything that is a metric can be followed, computed in the following paragraphs. Obviously, the figures I'm going to show you will appear to your imagination, mostly Euclidean distances. I'll talk about specific distances on the next slide, but I like to mention that all of the things that happen in this chapter and that go on work equally well if you have some function that only satisfies these things, which obviously means that what you are allowed to do and what you can do and what you need to do can be relatively limited. Okay, so here, like I said, some examples for some metrics, and these are probably the most common ones. So here's a figure that shows you a point P, and it also shows you different shapes. There's a blue shape, a black shape, and a red shape. These different shapes correspond to a unit ball in the respective metric. So you see the unit ball, that's a circle really. This looks slightly distorted because of the squares, but trust me, it's a circle. And this is a diamond, and that's a square. Now, these distances here, this way of geometry, have natural reasons. I mean, this is the black circle here is the classic Euclidean distance, which is, you can take a compass here and rotate that. That has of course a certain way of being defined. The Euclidean distance is nothing else but the square root of the sum of the square of the x distances plus the square of the y distances. There's a certain theorem here behind it. Again, classic Greek. That's sort of a standard distance where a space is isotropic, and regardless in what direction you go, it's always sort of the same distance, not distorted by any orientation by axes. Now that's not the only way, because here's a second one, that's the Manhattan metric. And the Manhattan metric is phrased that way, is called that way, because when you move in Manhattan from x to y, you go along avenues and streets. So you have a sum of the y differences and the y distance and the x distance. You need to cover the y distance and you need to cover the x distance. And the sum of that is called the Manhattan metric. And you see the blue ball here goes, that's one in that direction and one here. But you can also go here, then you have the same x plus y is always a constant. So this line here, all these points have the same distance of 1 from the center point. There's a third one which is frequently used. That's the maximum metric, and that's the red ball. This red ball says, okay, the x distance is at most 1. The y distance is at most 1. As long as none of them is bigger than 1, you're okay. You're inside of that unit ball. And you see, obviously, that's sort of what happens. You can, again, define that in terms of linear algebra and looking at the absolute values of these distance differences of the x values, y values, and take the largest of them, and that's exactly this kind of ball. That can be generalized. In case you haven't seen this, you learned this in math, but these are special cases. So you see here's a square root of something which gets squared. Here is a sum, and here is something, well, you take a max. There's a way of generalizing that. That's called p metric. For the p metric, you basically do something which is similar to here, except that for Euclidean distances, you take an exponent of 2, and then you take a second root, a square root. And here instead you take the pth power, and then take the pth root. So p equals 2 is that. And then when you look at this and you take basically, when you let p go to infinity, you get the maximum metric, because then the maximum dominates. And if you take the absolute values here instead, that's sort of the L1 metric. And you can convince yourselves that all these properties here holds, that yeah, there's a few extra things that you can look at and learn it in mathematical geometry. Okay, now maybe not all of you are interested in all these finer details of math, but definitely there's a place in the Marvel universe for a superhero dealing with this problem of that chapter. Remember in the last chapter it was convex Hulk, and here we have it's called closest pair. Thank you for groaning. Too bad I cannot listen to you or watch your faces. Okay, see, that's the closest one. All right. We will see in this chapter again that solving recursions here is of crucial interest. We did already have a few of these in the last chapter on convex hulls. There was a few things that I basically snuck by you. We did this sort of manually, or something I said, yeah, you can do that, and so on. But let's look at this a bit more carefully now that we have another example, and we'll look at this again today. And that should give you a bit more solid ground for other purposes. All right, remember this slide here, we've already seen it twice. I promise you will not see it next week, but that should be enough. There's quicksort or merge sort. These are divide and conquer algorithms that split the problem into some subproblems. We'll do some divide and conquer today again. That's a fundamental, interesting approach, and it's fundamentally powerful as well. You're dealing with a superhero, so you need superpowers. Divide and conquer. We also had another example in the last chapter of divide and conquer. There was this Preparata and Hong beautifully typeset paper from 1977, which was also based on merge sort somehow. And merge sort, yeah, we know that. The idea was you split the set into two parts. You solve the problem here, you solve the problem here, and then you put these two things together, right? So that is something we'll do again today for closest pair. So it's good to sort of see several examples of this approach because it is really powerful and it is very natural for many, many of these problems. Getting these things right is, of course, the fundamental question here for this divide and conquer, Preparata and Hong. There was the issue, okay, well, how do we get this merge step right? And there was this issue, how do we get this merge step right? And here you see we had written down this for the runtime. Now, I didn't do this in detail. I waved my hands over this and says, yeah, you get these tangents, and you can do that in linear time, here, linear time, and then you get an n log n. Two things. Where does this come from? We'll look at this in a moment. And the second thing is, well, getting a merge step in theta of n in order to get n log n is again something we'll do today for this problem of closest pair. And that gets us to this fundamental theorem, which is behind what you saw on the last slide in that lecture, in that other problem in this other algorithm. And let me show you. Here is a theorem. This is the third theorem of this chapter, or I mean the third item in this chapter. We had a definition, This says, okay, so we have a function from n to r, and this function looks like, well, you have here, the function of n is somehow defined by something t of, well, also again something times n. Let's look at this in a second in the next line. And then here you have some theta of n to the k. Now, these are numbers, real numbers, between 0 and 1. What does that mean? It means that the n here gets cut down to something less than n, something between 0 and 1. How can this occur? Well, that's a typical thing that happens in divide and conquer. You have your problem of size n. That's the runtime of a problem of an algorithm that's run on a problem of size n, on an instance of size n, and then you did some divide and conquer magic, cut it down to smaller subproblems. See, this is less than 1, so this is less than n, and solve these. Solving these is something you do recursively, but there's some amount of overhead that you have here, theta of n to the k. So in order to do the cutting up, dividing, and the merging, conquering, combining, whatever, is something that incurs a certain cost. Cutting this problem up into subproblems of smaller size is a very, very general approach. Usually what we will see is, yeah, there's a certain way of splitting the set, but it doesn't have to be. For a more complicated problem, you can have a subset of a smaller size here, a subset smaller size here. They may overlap. So the sum of these alphas may be maybe more than 1 or whatever. And this fundamental theorem tells you what happens with the runtime. Because all you need to do, you don't need to worry about what the algorithm is, whether this algorithm does certain fancy things. All you need to do is look at this equation, look at these parameters and this exponent, and then do a little bit of calculation, and you will get the complexity of this recursively defined runtime. Because all you need to do is look at these parameters to the kth power, that has something to do that this kind of overhead that you incur for every recursion step has an impact on the size of the problem, and you look at the kth power of alpha I. This is what you do here. You see alpha I to the k. Bang, bang. Well, here's the k. We'll talk about the c in a second, to the k and whatever. And there are three cases. This is a case where things are small, where the size of the problems drops relatively fast. And what that means is that the recursion is very efficient in sort of reducing the problem size and getting to an end. And in the end, the most you pay for is this overhead parameter at each recursion step. Okay, so that dominates, and this drops so quickly that it disappears relatively rapidly in terms of runtime. There is another, which we'll not talk too much today, but here that's something relatively interesting for other kinds of complex, difficult problems. That is when the sum of these kth powers of the alphas is larger than 1, because that means it's really hard to break this down. It's really hard to make the problem smaller. It takes a lot of time. And if that is the case, then this part here really dominates. This really dominates, and you get some funny number n to the c, where you basically need to do some magic with logarithms here to see that there's a cth power, which is larger than k, to get this to 1. And this is typically a situation where you get some really weird runtimes. So you can have algorithms that have a runtime, recursively defined algorithms that have a runtime which is not a polynomial really in n squared or cubed or something like that, but you get some n to the 2.093 or something like that, which is the result of that because you need this number. And then there's some, like I said, there were probably some logarithms involved, and that's where you get these crazy exponents. But our main attention here for the next slides and for this lecture today and for the algorithms that we're looking at is this one here, because this is where you get the sum of these kth powers of these coefficients here to be exactly 1. And what that means is that these two parts are relatively balanced, intuitively speaking. And we'll look at this in specific examples, some of which you already know, on the next few slides. What that means is that you get that overhead complexity times a logarithm of the n, which is the result of a tree, and you'll see that in a second in figures, so I'll not spend too much time on it, but you just get a logarithm times that. All right, so remember this, we just had that. This was from the Preparata and Hong, and you see this is an example of that up here. You see the t of n, right, and you see the 2 times t of n over 2. That's after splitting into a left part and a right part. And then you get some f of n, which is for splitting into left and right. And here's the interesting part. That's the merge part with f on n is this. I mean, that's basically what you do when you do the median and you split it up. We'll see why we can compute the median in linear time in a couple of slides. So that is the time for merging right and left. And if you can get this in linear time, then you see you have 2 times t of n over 2 plus something linear, and that this is 1/2 and 1/2 in this setting here. And what's the exponent? The exponent k is 1, so you get 1/2 to the first, that's 1/2, and another 1/2, that's 1. So we're precisely in this case, so we get n to the 1 times log n. So that is the reason why, if we can get the merge step in linear time, we get an n log n overall. More on that. Now, a bit of space up here. In merge sort, you see what happens here in merge sort. You get the same kind of recursion. in merge sort, again, you have T of n. So the time for sorting all these with merge sort is the time it takes for sorting that and doing the overhead of dividing and combining in linear time. So the critical thing is that you can combine this left part with that right part by always looking at the first pair and just taking the smaller of them, and that's sort of a standard thing. We'll encounter that again later in a geometric setting, but you see that's exactly another example where merge sort gives you an n log n, because here you have that. Now, I promised you a figure for your intuition, and this figure here basically does the following. You start out with n, so that's c times n, and then you split it into 1/2 at a cost of c times n, see that, and then you split each of them. That gives you a cost of c times, well, that's n over 2, and that's n over 2, so you get c times n over 2 plus c times n over 2, and then you get c times 4 times c times n over 4, that gives you c times n, and so on and so on. How many levels do you get? How deep does that tree get? Well, you're cutting it in half at each step. How many steps? How often do you need to cut it in half until you get to a leaf? That's obviously the logarithm of n. So the depth of this recursion tree is logarithmic. At each level, it costs you c times n. That's the overhead here. And you have a logarithmic number of levels. So that's intuitively a good way to look at this and a good way to understand how you get the logarithm in here. So in that case, see that again, that's always the same. Now, getting a 1 for these coefficients, the sum of these coefficients, there's more than one way of getting it, not just by 1/2 and 1/2. In fact, if you look at a recursion like this, so you see 9 over 10 times n plus 1 over 10 times n, and you look at these, and that's c times n, so that exponent is 1. So 9 over 10 to the first and 1/10 to the first, that's again exactly 1. So that means you get again a runtime here in that case, and that means you again get theta of n log n. And the reason is this tree that you have here, it looks not so beautifully balanced. It's sort of a little skewed to that side because you get 1 over 10 here and 9 over 10 over there. But you always get a certain fraction on that side, you get a certain fraction on that side. And when you keep going down that tree, at each level, you're only having 9/10 of what you had before. So even if you always take the bigger, deeper side, overall, after a number of steps, dividing by 10 over 9 or taking 9/10 of that, you will get to a unique leaf, and so that you still get a logarithmic depth of the tree. It's a logarithm not to the base of 2, but a logarithm to the base of 10 over 9. So yeah, you pay with a certain constant, but the constants are there anyways. So you still get n log n, even if you don't get a perfect split, but a split which has sort of a guaranteed minimum size. We'll get to that in different contexts later on. So that's the power of this theorem and the power of that case. You don't necessarily need to achieve a perfect split, something which is sort of guaranteed lower bound for the smaller one is also enough, or upper bound for the larger one. All right, medians. What's a median? A median is if you have a set of points and you look at the x-coordinates, then it's one which is in the middle. Actually, you see that's really a set of numbers that I have here, because we're just looking at the x-coordinates. And when you look at these x-coordinates, this is 1, 2, 3, 4, 19 numbers, and here is number 10. So that means on one side, I have not more than half of the points, and on the other side, I have not more than half of the point, which means that, intuitively speaking, this is a point which is right in the middle. Medians are important and interesting for distributions. When you talk about data science again, a median usually corresponds to a distribution of some sort, you may know that there's some median shows up, for instance, in median income, not average income, median income, and when you have a median, which really differs a lot from the average, that is a sign that you have an imbalanced distribution and so on, but that's a different kind of topic. Anyway, so here's a certain number, here's a certain number, and how can you compute this median? That's a fundamental problem of many contexts, so algorithmic problem. We'll make use of that as well. And you see there was a paper by Blum, Floyd, Pratt, Rivest, and Tarjan, 1973, that does this. Computing this median is not so difficult by just sorting. You can just sort these numbers, all the x-coordinates, you sort them. That takes n log n, okay, fine, we'll get that again in a moment. And then once you have them sorted, you can just count to the middle. But sorting itself, n log n, may already be a little too slow. And it turns out you can do better than that. You can do better than n log n. The answer is, indeed, you can compute, that was their insight, you can compute the median for n numbers in linear time. Again, we'll look at lower bounds in a few minutes. But it means you can do something fancy, something absolutely non-trivial. You can find the middle faster than you can sort these things. So sorting and then looking at the middle is slower than doing something fancy by some of these well-known famous colleagues. Rivest is somebody you know from RSA, and Bob Tarjan is the king not of the jungle, but of the jungle like data structures, and he's an absolute master of those things. Lots and lots of really fancy stuff to speed things up. Okay, how do we do this? Here's the paper. You can look at that paper. I'll post that paper again. Read that, compare to what I'll tell you. Obviously, there will be some figures here which should make your life a little faster. Let's see what we got. And I'll describe these steps relatively quickly, and I'll illustrate them with a few figures which give you some intuition. So the proof idea is this. You start with a set of numbers. So this is a set of numbers. Here you see them. They're not sorted, definitely not sorted. This is actually, when you count them, it's a set of 25 numbers. And these 25 numbers are not in order, but the first thing that you do is you group them into sets of 5. Okay? Let's do that. Here they are. You see this is 1, 22, 10. So you just take the first 5, bang, 4, 10, 5, put them down here. Take the next, put them down here. And you keep going and going. These are the groups. So these are the groups of 5. Fine. How long does that take? Well, O of n. Because all you need to do is go through the numbers once, and every 5 you just stop the set. If it's not divisible by 5, this whole set you can round, and that's not a problem. You just have a set which is subset which is a little smaller. Okay, second step is you sort these sets, each of these sets. How long does that take? Well, it's 5. 5 is a constant. You can use your slowest sorting algorithm for a set of 5 numbers, and it's still going to be constant because you're dealing with a constant. Obviously, you shouldn't use your Bogo sort or something like that, or Bogo sort, but use a reasonable sorting algorithm, and it will take constant time to sort any of these subsets, and you get these quintuples which are sorted like that. Bang. So you see this is all sorted by size. Okay. How long does that take? Well, we got n over 5 of these tuples, and every one takes a constant amount of time to get sorted. So again, we get linear time for that sorting. All right. So far, so good. That was easy. Anything takes linear time, but we only have linear time total, so we shouldn't wait a long time. Now comes an interesting step, because this is actually something where we use recursion. You see, with these sets of 5, you have a middle number. That middle number is a median of each set of 5. Here we have it. And those ones. And now you compute the median of the medians. So look at all these middle numbers, and for those you compute the median. Well, we are computing the median, but this is a smaller set. So we started out with n, and how many do we have now? Well, we only have n over 5. And that we compute by using a famous algorithm by Blum, Floyd, Pratt, Rivest, and Tarjan. We do it recursively. That takes t of n over 5. Same thing here, okay? We're not done yet, but this will be done. Okay. Now, once we have this, we look at this set again, because we will use the median of medians as the pivot to reduce the set of numbers. I'll show you that in a second. What's the median of these medians? So you've got 9, 11, 13, 14, and 18. So that's the median of the medians. And you see that's in here. We've sorted the columns, the sets, the subsets, so you have a better, an easier time of finding this. Okay, so here's the median of medians. Come on, you. Here it is, okay. And now, when you look at this, you see that these numbers to the left, in the middle at least, are smaller, and these are bigger. And then there's some which are smaller than these, so that quadrant here consists of all numbers which are smaller, because these are smaller because in the same set, these are smaller because this is in the median, and these are smaller because they are smaller than this. So this set of numbers, this green, none of them is bigger, which means when you look at the median, well, you know, you can say like, you must have at least a quarter of the numbers which are smaller. And by the same token, you can look at this and you see, well, you know, there's a certain set of numbers which are definitely bigger, and you see here's a set of numbers which are bigger. So that's that. You don't know anything about these other numbers. They may be bigger or smaller, but regardless of what you do, regardless of how you split this, regardless of where the median of medians is in the overall distribution, that's what the pivot is, like in quicksort, you will have at least a quarter on one side, at least a quarter on the other side. And if you look for the global median, the one which is in the middle, you know that the smaller size, the smaller side, you can eliminate and look for an appropriately numbered position in the other set, which means you can discard at least a quarter, maybe more, but at least a quarter. And that means when you run the algorithm again after using the pivot on the rest, that you have gotten rid of a quarter of the numbers and you just need to do it on the others, which means that you do a recursive step which takes t of 3n divided by 4. So you see, we use it recursively here, we use it recursively there, and now let's look at this whole thing carefully, because that's what the total runtime is. You remember we had this linear overhead here for these, we had this for that recursive step, this for that recursive step, and yeah, that's the runtime, recursively defined. Now, you look at this again, and when you look at this again, you see, okay, what does that work out to? And remember the master theorem here. Okay, we need to look at that. There's a 1 over 5, and there's a 3/4, and the exponent, you see that's a 1 again. So you see here you have 1 over 5 plus 3/4, that's 0.2, and that's 0.75, that's a total of 0.95. 19 over 20, which is wonderful, because we see we're in this case here less than 1, that is less than 1. And that means the total runtime for this algorithm works out to being linear. And you see that from this master theorem easily by doing the right kind of recursion. And if you want, you can look at this original paper and you can look at the numbers And you can look at why a 5 works out well and whether a 3 or a 7 would do the trick as well. I'll leave that to you. The important part is this one here, and then you get it. So that is exactly what you get. Linear runtime faster than n log n. Nice. So now, of course, you could argue, well, maybe we can do the sorting a little better. Maybe we can do with an idea like this median that works so great. Maybe we can sort of do recursive median computation in the right way, and we get something which is better than n log n, which is what we look at in lower bounds. And then we're generally gradually getting to closest pairs. So that is something you may remember. We did use it again already in the convex hulls, where I showed, so we know there's a lower bound and because of the curvature and so on. But now to refresh your memory and to sort of expand this, how does this work? And that's also, again, I mean, you may say like, well, you know, you're not presenting these things in a linear order. You could have done that earlier and all the basics. But that's not how research works, because people go back and forth between ideas and papers and previous results. Timothy Chan in the 90s looked at some stuff that people had done in the early 70s. And so more advanced ideas are often based on previous ones. And that also means that when you sort of try to push this a little further, you look at the details again of the old stuff and see if you can maybe modify something in the proof, expand, generalize some of these ideas. And that's why I bring this back up, because that's typically what you do when you try to push the frontiers of science. You look at the old records and look at how you can use them. So let's look at that. Sorting has this lower bound. Why is that? Well, the first thing is when we have a set of possible permutations of a set of numbers, and we're only allowed to make pairwise comparisons. Initially, we have n factorial, and every comparison we make gives us 2 possible answers. So set of permutations where this one is smaller, set of permutations where this one is smaller. And in the worst case, the larger set remains. We get the answer that we don't like. So the best we can hope for is to bipartition of a set of permutations. So that's the best we can hope for, half the number of permutations. And remember, we could also, if we get a balanced partition where we, in each step, get rid of a constant number, but we cannot hope to do better than a factor of 2. All right, and so until we get a unique permutation, we need to cut this in half until we get this unique permutation, which means we have identified this sorted, unsorted order, and that's a log of n factorial. And when you look at the log of n factorial, that's now easy. You see the log of n factorial is nothing but the sum of these logs of numbers from 1 to n. And then you can do a couple of estimates, because if you just drop the first n over 2 terms, basically you say, let's not worry about the small stuff, let's start with n over 2. And then let's not worry about the big stuff. I mean, nothing, none of these here is, all of them are bigger than n over 2. So if you put an n over 2 here, you get something which is definitely not bigger than that. So only take the first, make something smaller, reduce that, replace all those by n over 2. Then you get n over 2 times log n over 2. And when you look at n over 2 times log n over 2, that's n over 2 times the log of n minus 1. And when you look at that, you see easily this is theta of n log n. Bang, here you go. Easy. So that's the set of numbers. You have some operations which reduce the set of remaining candidates. And in the end, you need to identify a unique one, and that gets you the logarithm of this, so that gets you n log n. And at the heart of this is basically, the reason is that n factorial is actually quite a bit bigger than 2 to the n. The log of 2 to the n is n, whereas the logarithm of n factorial is considered bigger. It's n log n instead of just a constant times n. All right, this idea, like I said, we're revisiting this idea that you've seen before, or maybe we've used it before. Let's look at that in the context of these geometric problems that we're interested in. And you see here there's Benor from 1983, so this was after some of the things. It was actually after the main algorithm that I'm going to show you today. Something about lower bounds. And here's the paper, or the theorem for the paper, which interests us the most here. Computing a closest pair for n numbers takes at least omega of n log n. In other words, regardless of your fancy recursions, regardless of your fancy applications of master theorem, regardless of computing medians and linear time and so on, you cannot hope to do this better than sorting, fundamentally better than sorting. And that's of interest to us, again, because then we don't have to worry about it once we get an n log n algorithm. Now, it's worth looking at this because this kind of lower bound applies to a whole number of different problems and a whole set of a whole family of different approaches, different models, really, because we're looking at models of computation. The model of computation for sorting was pairwise comparison. Obviously, you can do a few more things. One of the things that you can do in geometry is, of course, draw circles, lines, stuff like that. And as some people have observed, of course, we've observed again, there's some linear algebra when you go from vectors in space to numbers. And the same thing applies in Euclidean geometry when you draw circles and parabolas and things like that. These are quadratic polynomials, quadratic curves. And when you do intersections and so on, you solve some equations or inequalities on these kind of terms. So what Benor observed and proved, and it's a pretty nifty paper, any algebraic computation tree that solves the n-element distinction problem, distinctness problem, n-element distinctness problem must have a complexity of at least omega of n log n. So there are a few terms here. Algebraic computation tree, what is that? And what is element distinctness? Well, element distinctness is not so difficult to understand. Element distinctness is, I give you n numbers, and I want to know if there are any two which are the same. Or, alternatively, they are all distinct. If you do the sorting on these numbers, sort them, and then go through them and check if you get any two consecutive numbers which are the same. So after sorting, again, it's easy in linear time, but you cannot avoid doing something which is of basically the same kind. We'll get to this, why this is of interest for us in closest pair. So let's look at this step by step. Basically, the idea is you can look at the paper and you will see, there's a certain amount of depth in that paper. So, algebraic decision trees. I did not mention what those are, but let me throw a figure at you here. This is not my figure. Here's a credit in the corner. Basically, when you do a binary search, you say, like, is this less or is this more? Is this better, smaller, or larger? So on. We did the binary search for chance algorithm, of course, where you say, like, should I go left? Should I go right? That's a simple answer. But instead of doing that, what you could also do is do something which is algebraically a little more difficult. So you see there's something quadratic here, and then depending on the outcome, you go into one of these branches. It's not just two branches, it could be three, like greater than 0, equal 0, or less than 0. And then you, depending on the decision, you go down here and you do these kind of things. That's sort of what an algebraic decision, the idea of an algebraic decision tree is. So you have some algebraic term which you evaluate, you go down one of these branches depending on the outcome of that question. And then, of course, you do a sequence of questions that you ask, make a sequence of decisions. For instance, does that point lie inside of that circle? Which is something you could do for evaluating distances. And then depending on that, you sort of keep going down this way. Now, the next thing is, when you have a set of numbers, these are n numbers, and that's a point in R to the n. Basically, every number is a coordinate in a different dimension. And then when you look at element distinctness, that's basically the idea in Ben Orse. I mean, so that's what he's arguing. And then there's some corollaries like closest pair, which you see in a second. Okay, so that's part of a more general setting. You don't have just a discrete set of points, which maps to one point in R to the n, but you have the whole space, which is basically all the sequences of n numbers. And so there's a certain structure which they share. So when you have a property like these are n distinct numbers, then you can look at all subsets in this higher dimensional space which share the same membership property. For instance, everything is distinct. They're all distinct. And well, what are point sets in this high dimensional space where they're not all distinct? For instance, a hyperplane where something is the same. And when you look at the connected components in this set, which is sort of different ways, like different permutations, different connected components in this high dimensional set, you can show that the height of an algebraic decision tree is something like that. That's the number of connected components. That's the number, Carnelli of numbers. And there's a theorem in Ben Orse's paper that basically you see there's some log of n minus n. There's some slight variations in the notations that should not throw you off here. Now, element uniqueness in that setting, in this way of interpreting that problem, you can show that that has many connected components, just like permutations has, but this is a more geometric setting. So many connected components, and then when you take the logarithm of that, that gives you what I showed you in the beginning from that paper, n log n as a lower bound. And now I do the final step and I say, well, you know, element distinctness is really, if you have two numbers which are the same, then you have a distance of 0. That's element uniqueness, element distinctness. And of course, you could do that by rounding to a certain extent. So you could have a magic number that says, like, are there two numbers which are closer than an epsilon or something like that? And then you no longer have them distinct if they're really close together after rounding. So basically having a really, really small minimum distance maps out to having them the same. All right, time to do something constructive. So far we showed we cannot do it in faster time than n log n. Now let's do that in n log n. And there's some easy observations. First of all, if we do this not in two-dimensional space, but in one-dimensional space, then it's really easy to do that in n log n, because all you need to do is you sort the numbers, and then you run through the sorted list, and you keep track of the distance between consecutive numbers. If you have consecutive numbers, you just remember the smallest between consecutive numbers in that sorted order, and that will be your minimum distance in total. And you can try, of course, n log n. That's what we do. We cannot do better than n log n, so that would be great if we can do that. You could try to do the same thing, like sort them by x coordinate or y coordinate, and try that. And see, like, yeah, okay, if they're really close in x, maybe that's a good pair of candidates if they're really close in y. And you will see that this doesn't necessarily have to work, because here you have two points which are close together, but they are not close together in the sorted order, because these are neighbors in the sorted order. But even though the x coordinate is really very similar, the y coordinate is hugely different, so that distance is large. And the same thing here. So in the y order, you see here's these two are in between those two in the y orders, but they're still very far apart. So there can be a whole lot of stuff between these in the sorted order, regardless of x or y. And that means you cannot just look at the coordinates and say, yeah, fine, I'll just use the sorted order that way. We need something better, something smarter. And of course, that's what we're hoping for, because we're not looking for an easy way. We're looking for ways for things which are not so obvious. Okay, and that gets us to the next paper, Bentley and Seamus from 1976. Here it is, the original paper. And again, you can look at the original paper from the website. Let's look at what they're doing. Now, after all these preliminaries, after all these explanations, after talking divide and conquer and these kind of things, basic idea is this. You have a set of points. This is two-dimensional. We want to get something in n log n in 2D. Okay, divide and conquer. Let's cut this in half. We use a median line. Here's the median line, bang. That's a median point by x coordinate. And now, in the same spirit of before, we have a set of points on this side. That's the median line. There's n over 2 points up here, n over 2 points up here, at most n over 2. That's a set of A, and that's a set of B. Using A and B here, that's original from Bentley and Seamus. You will find that notation in their paper again. All right, and now we solve this with our magic recursively working algorithm on this set. What's the closest pair here? I think this one is a good choice. Solve the subsets. That one here, bang, you see that? And already here you see 2 times t of n over 2. Yeah, point sets of half the size using that algorithm again. This here has a distance of delta A for that side. And let's look at this over here. What's a close pair? I think that's a good choice. And that's a delta B. There you go. Closest pair on that side, closest pair on that side. Almost done. The only thing that could happen, so if we have a pair of points in here, we know it. Pair of points in here, we know it. It could be that we have a pair where one is on this side and the other is on that side. Okay, let's deal with that. First of all, that's the smaller one of these two. Yeah, so let's take that as delta. And now we will just look at these two sub-problems, merge, you know, like in merge sort or some of these other things we've done, and just look at this. That shouldn't be so difficult because we know we only need to look at points on the left side which are within delta of this line. And we only need to look at points on the right-hand side which are within delta of that side again. So that's a strip of size delta. And that's a strip of size delta. Come on, you strip. There you go. All right. So take a point from this side, take a point from that side, find the closest pair within this narrow strip. How difficult can that be? Well, you know, all we need to do is do it in O of n. Yeah, okay. But it's still possible that you have a linear number on this side and a linear number on that side. It could be as many as n over 2. Could be maybe n over 4, but still a linear number. And if you look at all these pairs, you haven't made much progress. Something in this strip, something in that strip. Could still be a quadratic set of pairs that you need to check, and that's too slow. I mean, that's not even n log n for looking at all these. We want n for solving this subproblem. So we need a few extra ideas to get this to linear time for dealing with a point from the blue and a point from the green and find the closest pair that combines these. That's what we want. Okay, let's make a bit of space here. And this is actually a figure, a critical figure from the original Bentley and Seamus paper. I'll run you through the details and I'll give you some idea, some more dynamic ideas. What is the argument in here that you can do this actually? So here's a bit of space in here. And now let's look at a point which is on the blue side, on the left-hand side. Now, all these points over here, they must have a distance of at least delta. So that means you cannot have any 2 points in the green which are closer than delta. They must maintain a certain distance. And that means they are spaced apart. Now that also means that any candidate for this as a neighbor must be either on one hand must be within delta of this, but it also must be apart from each other, which means, see that figure here, that means in this setting here, you cannot have more than 6 candidates for this point, which are candidates for being a closest pair like this one here. They're really close. So that would be the answer here. Here's the thing. Because if you look at balls of size delta over 2, and I'm drawing this here with axis parallel, like that's the max metric, but you could draw this with other balls of other metric, axis parallel, whatever. But these balls here must be distinct, must be disjoint, because you need delta over 2 to get from the center point to the boundary, and then from the boundary to this one. So triangle inequality tells you like they better stay disjoint, these balls, because otherwise the centers are too close. Now, you can only pack so many inside of a strip, the centers, that they don't overlap. Only 2 here, and at most 3 here. That's exactly the delta here, and the 2 delta here in the original paper. And you see you can have at most 6 points within range of delta of this particular point. Everything else is too far away and is no longer candidate, and they cannot be more bunched in here because they would be closer to each other than delta, and that, by assumption on the recursion, doesn't happen. That is very helpful because we know now that for each point we only need to check a constant number of neighbors. So let's write this down quickly. No point can have many close neighbors on the other side. When I say many here, I'm arguing 6 here, but of course some of this generalizes to higher dimensions, and then it's not 6. It can be a different number, like 18 or so in 3D. It's a constant always, and regardless of what you do, don't get too many of these neighbors. Now, what I just said already, packing argument for these delta over 2 balls works also in other fixed dimensions. So this basic idea is very general, very universal. You don't have to draw it for every metric. You don't have to draw it for every dimension. It's sort of a general idea that works there. There's the packing, basically. Okay. How does that help us algorithmically? Let's look at some more general situation here. And what we can do is, when you go through these points here, from top to bottom, like that, then there's some sorted order by which you look at these points. So you keep track of potential neighbors, so let's look at that. So when you look at this point, any potential close neighbors must be within this union of 6 balls. And when you sort of go to the next one, you scan down here, you look at the next one, you scan down here. So you basically see you can, by just going down track here, keep track of these. And notice that this is somewhat in spirit and in flavor similar to the merge step in merge sort, where you have 2 sorted lists and you compare them pairwise and see like which one is bigger. Here you look at this is sorted by y coordinate, this is sorted by y coordinate. You run down here, bang, 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 you run down here, bang, bang, bang. But you only need to look not at 1, but at a fixed number. So you go down here and then you keep going like that. You scan through that same set, and doing that is relatively straightforward. Okay, good. Now, I was saying you run through these in order, you sort them, you run through these in order, but you should say like, wait a second, what's happening here? You sort them. When you sort them, it takes O of n log n time. So that's for the merge step, you take O of n log n time. So if the merge step, that means that every level of this recursion tree, you get n log n. The recursion tree has depth log n. So you would get O of n log squared n. Now there's one thing to observe. You don't need to sort them for every recursion step because these are part of a bigger set. This is just a subset, a sub-problem. And when you look at the sub-problem, you see if you do a global pre-sorting in the very beginning, so then you have a sorted order of all the points, then in order to compute the sorted order of these, after you have sorted the global set by y-coordinate in this case, all you need to do is basically run through the sorted whole set and then basically pick up these points in the order which you have and that you can do in linear time after the pre-sorting. You do that once, and that will work for every recursion step, and you can do that in linear time on both sides. So global pre-sorting gives you O of n, and that means total time is n log n, which is wonderful, exactly what we wanted, which means that we're good here and we can rejoice. But one more thing, couple more slides, and we got just the right amount of time here. That was in 2D. So remember, doing this in 1D was easy. We just go through the sorted order. In 1D, in 2D, we do the recursion. Dan asks whether the median is handled at this stage. The median is handled for doing the subdivision, for the split. So you have your set of endpoints, you compute the median, and then you do a split into n over 2 and n over 2. And then that's for the splitting. So divide, recursively conquer, and then combine. And the combined things that we were concerned about, okay? Could it be part of the closest pair? Yeah, that's not a problem. I mean, then you need to sort of assign it arbitrarily to one side, to the left-hand side, and so on, but that still works for Dan. If there are more questions on this, we can follow up on this after I've finished with these next two slides, so we're in time for everybody else. I'll stay around there. All right, higher dimensions. We had n log n by sorting on a line. We had, after a bit of squeezing, so if we didn't do this pre-sorting and use that trick, we got n log square n. We can use the same idea in higher dimensions. And here's a nice figure that I stole from Subhash Suri's slides on this topic. So instead of using just a line, you use a hyperplane that cuts the set into two subsets of basically the same size. Could be a median line to some coordinate. That's something to revisit in a couple of moments. Now what happens is when you do the merge step, let's look at the merge step here. We have a slice, a slab of width delta. Before that was a strip. Now this is a sort of a slab. And instead of a strip, basically the strip then was sort of had a linear structure, and we could run this through as a one-dimensional problem again. If you basically do away with that dimension, you have something which is one dimension lower, which is cool because then you can solve the problem in one dimension lower. And that means you get this kind of recursion that says you solve the problem in d dimensions by solving two problems of half the size in d dimensions. And then you have, there's some overhead for maybe median computation or sorting these things in the appropriate sets and so on. And then you get a sub-problem on the slab, which is one dimension lower, but it can be sized linear in this. So in that recursion, when you look at that, I'll skip all the details on that, but we know that there's something that happens here in n of log n to the d minus 2, because basically, you saw what we just did. We reduced, we were able to strip away two dimensions by this idea with a sorted order in 2D, 1D, and so on. So you save here two exponents. But when all is said and done, you get this here O of n log d minus 1. So that's after sorting. Remember, after sorting, the one-dimensional linear problem can be solved in linear time, and this one could be solved in n log n. And if we go to 3D and we don't use any extra tricks here, just that, then we get n log squared n, and so on for higher dimensions. But there's one more trick, and that's a bit of a magic trick, at least for the purposes of today. This magic trick is basically this. So if we can make the problem size after doing the recursion step a little smaller, not just linear, but we save some logs here by dividing through that, then we get a better recursion here, and then we get to n log n. And this is actually a theorem here in the paper by Bentley and Seamus that says, yeah, there's something where we can reduce the size of this sub-problem where you get these packed balls, this sparsified problem. And we can save a little bit here by looking at this from the right angle, the right way, and that gives us a better recursion here. So you need, when you do the subdivision there, slightly trickier, slightly niftier, you just don't do any coordinate and any median, but you do something slightly trickier. And when that is done, there's an extra theorem, this could be a lemma, that says, oh yeah, there is something that you can do. The number of points that you're left with is not linear, but it's less than linear. So you see here the log, here's the log, and the denominator, which you save, and then when you do all this, you can do that in linear time. Then you solve the recursion. And this is a figure in the Bentley-Seamus paper about that. And you see there's some fancy math going on here with some non-trivial denominators looking at this slab. There's a slab that has few points. And that turns out, some details here, basically, if you have such a slab which has a little bit less than the linear number of points, then you solve this. Then you see that you got that and that. So that's no longer n log n or something with a power, but that's linear again. And then, of course, you get this. And that's exactly what is the theorem in the Bentley and Seamus paper. I'll leave it at that for today. I'll leave it at that hand waving for this higher dimensional thing. You get an idea here, and you get also the idea that there's some basic algorithmic paradigms, divide and conquer, evaluating these recursions, the runtime of those, combined with some geometry that allow you to push these frontiers, and that's a fundamental approach in computational geometry. Look at the algorithms and the math in combination with the geometry, and then you can do things which sometimes generalizes even to higher dimensions, possibly with an extra trick. That's it for today. Thank you very much. See you around. Please take note of Christian's emails regarding homework problems, assignments. Also follow up on the emails we're sending about the papers if you want to look at them. And now I will stay around in the chat and answer questions. I will stop this, this recording, and I'll answer to Dan when whoever else is around by, back into the light, in the chat. Thank you. See you around.